This is a short lecture on recursion. My name is Alan Doran. Some of the subtopics we'll look at in this lecture include subdivision, recursive subdivision, and computation of the factorial function using recursion. Here are a few questions you should be able to answer before you complete this video lecture. If you find you can't answer one of these questions, go and revise that topic before proceeding. What is recursion? Well, it's convenient to start with a dictionary definition. It's a noun defined as the repeated application of a recursive procedure or definition. And then there's a joke which you'll hopefully understand before the end of this lecture. If you still don't get it, see recursion. One way of understanding recursion is to visualize the procedure. So when we think of recursion, we're actually thinking of what are known as self-similar structures. Self-similar structures are those that exhibit the same statistical properties at different scales, and you would have come across these in previous studies or even in everyday life. For example, here we start with a line and we continuously, recursively subdivide it to create a snowflake pattern. This is known as the Koch curve. And you can see as we proceed down these layers, each line segment within the previous line segment is subdivided in the same way that the very first line segment was subdivided. As we progress, we get finer and finer detail. But if we were to zoom in on that detail, we'd find at each scale the same characteristic shape. Here's another example of a recursive branching structure in this case, a binary tree. We're probably familiar with this from some of our other data structures we've seen in computer science, but even if you just look outside at the trees, you'll notice that branches are recursive structures. The main trunk in this little illustration divides in two, and each one of these branches then divides in two, and divides in two, and it divides in two, and so on until we're down to very narrow twigs. Here's a subdivision of an area. In this case, we're creating what's called a Sierpinski gasket. And we start with a triangle, and we subdivide that triangle recursively into 4 sub-triangles. Then each one of those we subdivide into 4 triangles, and each one of those into 4 triangles, and so on until we end up with a very porous structure, the Sierpinski gasket. Now, this is a process that can continue ad infinitum until we get bored of it, or until the computer runs out of memory if we're doing it in software. But it's a recursive process because we're calling the same procedure of subdivision again and again on the same structure. Now, if we are to transfer this understanding of recursion into software, then we need to look at algorithms. So a recursive algorithm is one that depends on its own execution for its solution. So here we've got a very simple recursive function. This one will recurse infinitely, just like we saw with, say, the gasket or the tree. And you can see we've just called it infinite recursive function, and the only thing within the function is a call to infinite recursive function. And if we have a look across the bottom of the image, we can see this calling stack, if you like, illustrated. So we start over here on the left, and we call the function, and when we reach the first line of the function, it's another call to the function, so the function calls itself. We then call the function again, and the function calls itself, and it calls itself, and it calls itself, and it calls itself continuously, in this case forever, because we don't have any way of stopping it. Now, usually what we do, if we wanted to solve a problem by using recursion, is to make sure that the recursive calls act on simpler and simpler versions of the problem until we're able to solve this problem quite easily. And then we can terminate the recursion and return back up the calling stack with a solution. So let's do a visual example here. Now suppose I've lost my slippers and they're somewhere in my garage, and this is what my garage looks like. It's a bit of a mess. Now if I were to start hunting for my slippers, there are a number of ways I could do this. I could just hunt around randomly in my garage and hope that I stumble across my slippers. But this of course would mean that I'd be hunting probably in the same place multiple times. I might even overlook some places and never find my slippers. So instead I'd probably like a more methodical way of searching the garage. One thing I might do is start over in one corner and work my way across the room or around the room until I find the slippers in a very methodical way. An alternative is to use a recursive algorithm where I subdivide the area up into smaller and smaller spaces. So to begin with, let's subdivide my garage here into 4. Now I've got 4 sections, each of which I could search one at a time until I find my slippers. Each of these sections is still quite large, so it would probably pay me to subdivide a little bit further. So I recursively subdivide each of these quarters into quarters. And now I look and I think we're getting there, but in some areas of the picture there's still quite a lot of things to search through. Maybe I need to subdivide each one of these 4 sections that have been quartered into yet 4 more. And here I've got a recursive subdivision that I've applied now 3 times. So I've got quarters of quarters of quarters. And I could start hunting through my slippers. Within each one of these, the problem has been simplified. So each one of these little sections of the original garage is now small enough that I think I could search it without missing anything. And if I were to do this, I would find, here are my slippers, over on the left there. And I could then return to my lounge room with warm feet. Okay, so let's include this termination condition, the condition where the problem is simple enough that I can solve it, into the algorithm. So here we've got a limited recursive function and it takes a parameter. And the parameter you can think of as, in the case of the slippers, defining the area of the garage that I'm searching for. Now, if the parameter is 0, that is if the size of the area I'm searching is very, very small, that is it's small enough that I don't actually have to search there, then when I look in that section, I can say, oh, look, I found my slippers. Now, if the area is big and confusing to search, then instead of starting to search it, I subdivide, or I call my search algorithm, if you like, on a smaller section. And by reducing over here, we can see the parameter by 1. In this case, I'm reducing the area, if you like, of the problem space. So I'm simplifying the problem. And this is a typical structure for a recursive function. So we have some parameter or parameters that get passed. We have a termination condition that says when the parameter reaches a particular value, the problem is simple enough that we can solve it easily. And if it's not, then instead of returning directly, we make another recursive call to our recursive function by passing it a parameter that is a reduced version or a simpler version of the problem. At the bottom of the slide now, we can see the calling stack. In this case, we might call our limited recursive function passing it a parameter of 4. Now, in this case, the termination condition doesn't apply, so we then call the recursive function from within the recursive function, but this time we're going to pass it a parameter of 4 minus 1, which is 3. And we do that again. The next time we call the function, 3 minus 1 is 2, 2 minus 1 is 1, and 1 minus 1 is 0. So over on the far right, we can see we finally call the method with a parameter of 0, and in this case, the method is able to return immediately. It doesn't need to continue calling itself recursively, and it returns the value 0. Now, it returns it to the previous version of the function, the one that called it, and this function has then finished, so it returns the value 0, which is again going to be returned to the next level up, back to the next level up, until finally we exit the stacks with the value of 0 and we've finished our recursive call. This isn't a particularly useful function, this limited recursive function as I've written it, so let's now have a look at something a little bit more useful. Factorial, written with the exclamation mark, can be calculated using a recursive algorithm. Here's a little explanation of how we can do this. So factorial 5 is defined as 5 times 4 times 3 times 2 times 1. In general, we can define factorial of some number n as being equal to n multiplied by factorial of n minus 1. That is, in the case of 5, we've got 5 and 5 minus 1 is 4 and 4 minus 1 is 3 and so on until we get to 1, which is the termination condition. And factorial of 1 is simply 1. So we're multiplying by successively smaller integers until we reach the termination condition, in which case we've got 1. Here we can see this illustrated. So the blue box is really the simpler version of 5 factorial. That is, the blue box is highlighting 4 times 3 times 2 times 1, which you'll recognise is just 4 factorial. So factorial 5 is equal to 5 multiplied by the blue box, 4 factorial. And we can keep simplifying this because 5 times 4 factorial is equal to 5 times 4 times 3 factorial. And that gives us a termination condition eventually of 1. Here's a representation of the factorial function written out algorithm. We can see at the top the termination condition. In this case, if n is less than or equal to 1, then the factorial function immediately returns with the value 1. Otherwise, as we've already explained, we call the factorial function on a simpler version of the problem. That is, in this case, we subtract 1 from the parameter, and we will return the result of the current value of the parameter multiplied by factorial of n minus 1. So that's our recursive call on the simpler version of the problem. Here we've got the algorithm again, and underneath it, visualization of the calls. So we see that 5 factorial is equal to 5 multiplied by 4 factorial. And this in turn is expanded to be 4 multiplied by 3 factorial. 3 factorial is expanded to be 3 multiplied by 2 factorial, and so on down until we end up with 1 factorial, which, judging by the algorithm, has an immediately calculable value of 1. We're then left with an expansion which we need to return along. So with 1 multiplied by 2, 2, and then 2 multiplied by 3, 6, and 6 multiplied by 4 is 24, and lastly 24 multiplied by 5, we're able to now calculate the final value of 5 factorial, which is 120, and this is the value that will be returned after we've completed all of our recursive calls. So that's it for this first introduction to recursion. Just remember that recursion is the repeated application of a procedure as a component of its own solution, and that usually, if we want to avoid infinite recursion, each time we recursively call the procedure, we do so on a simpler version of the problem until finally we're able to stop when the problem is simple enough that we can return an immediate result back up the calling stack. So that's it for recursion. If you still don't get it, run the video on recursion and have a look. Thanks for your time.